Hi, today I am going to talk about my practicum project. The task that I have been working on is the semantic image segmentation task to segment 3D brain sMRI voxels into white matter, gray matter, and CSF. My mentors were Janet from USF and Ashish Raj NC from UCSF. First, let's talk why this task. The segmentation will give us a feature map. The feature map is where each voxel in the brain sMRI is labeled as being belonging to one of the tissue types: white matter, gray matter, and CSF. And these feature maps can be used for various other purposes. So one way we can use this feature map is for different classification tasks, such as Alzheimer's versus normal, Parkinson's versus normal, etc., using transfer learning. We can also extend the model that produces this feature map for the regression task of predicting cognitive scores of the patients. Let's talk about data preparation and data preprocessing. The dataset was procured from ADNI. ADNI stands for Alzheimer's Disease Neuroimaging Techniques Initiative, which has the brain sMRIs of patients who are normal, who have Alzheimer's, and who have MCI. MCI stands for mild cognitive impairment. There were 1,316 brain sMRIs, each belonging to different subjects. The data was first pre-processed using skull stripping, bias correction, denoising, and normalization. Then I used FSS FAST, which is a segmentation tool, to assign labels of being a tissue of type white matter, gray matter, and CSF to each voxel in the brain sMRI. The rest of the pixels were regarded as the background. In order to improve segmentation performance, I also used different data augmentation techniques such as center cropping, vertical, and horizontal rotation. The images were center cropped to 128, 128, 128 dimensions. Let's look at one of the slices of the 3D sMRI volume, and on the right side we have its corresponding target with 4 classes. Each pixel on the right side belongs to one of the classes: white matter, gray matter, CSF, and the background. This is another of the slides of the sMRI volume. Now let's talk about the methodology. So I used a 3D symmetric unit model to do the semantic segmentation task. This unit model consists of 4 encoding and 4 decoding blocks. Each encoding block consists of 2 convolution layers with batch norm and ReLU activation layer. And finally, we have one max pooling layer after each encoding block. Whereas for each decoding block, we have one transpose conv layer and then 2 convolution layers with batch norm and ReLU activation layer. From each encoding layer, we have a skip connection to the corresponding decoding layer. As you can see, the architecture looks like this. These are some of the architecture details. As we can see, we have 4 contraction blocks. First encoding layer has contraction blocks are basically encoding layers. We have 16 filters in first encoding layer, 32 filters in second encoding layer, 64 filters in third encoding layer, and the last encoding layer has 128 filters. Then there is a conv layer with 256 filters, after which we have expansion that is decoding blocks, where the number of filters is 128, 64, 32, and 16 for each of these blocks. Finally, we have conv block that maps each voxel to one of the 4 classes. This model was trained for 56 epochs with batch size of 8. I used cross-entropy loss function and Adam as the optimizer with the learning rate of 0.0002. I chose accuracy and dice score as the evaluation metric for this task. Let's see some of the results. Uh, so the slide shows two of the slides of the segmented output of the 3D brain sMRI. The left one is the original image slice, the middle one is the model segmented output slice, and the right one is the original target slice. You see that the model's output is quite close to the ground segmented map. So in order to conclude, uh, these are the results that we have. Overall, my model achieved an accuracy of 0.923 for the segmentation task on the test set. The dice scores were as follows across the classes. The overall dice accuracy was 0.9166. For the similar segmentation task, but on different datasets, other works have achieved an overall dice accuracy of 0.93 using NeuroNet model and 0.89 using USegNet model. That's it. Thank you for your time, and please let me know if you have any questions.